It's exciting to come your way once again. My name is Nana Yawedu, and you can call me Sir Nana. In this lesson, we are going to look at additional mathematics, and we are considering number and algebra pattern. In our previous lesson, we've considered some symbols for binary operation, and we realized that symbols and variables are very important when we are dealing with additional mathematics in general, especially when we are looking at binary operation. Ensure that you subscribe to our YouTube channel so that you can get all videos on time. Get your jotter and your pen as we move on to this lesson. In this lesson, we are looking at a very important property of binary operation, which is the closure property. Now, when we talk about the closure property, we are looking at the property of binary operation where we are looking at two elements performing an operation to produce another element which belongs to the same set. So two elements. So we can say let x and y, which belongs to the set of real numbers. So the set here belongs to the set of real numbers, which is the set being spoken about here, right? And then we are saying that we can have an operation x operation y, for instance, right? Where x operation y can be xy plus s plus y. Now, provided that xy plus x plus y also belongs to the set of real numbers, then we can say that the operation here, the star here, is closed under the binary operation. So for instance, if you are using real numbers and we are using 2 and 3 as our numbers, we can have 2 operation 3, right? Where we have 2 multiplied by 3 plus 2 plus 3. So we will have 2 operation 3 to be equal to 2 multiplied by 3 gives us 6, and then 2 plus 3 gives us 5. So our 2 operation 3 will give us 11. Now, look at the 11. We realize that 11 belongs to the set of real number system. So therefore, we can say that the operation star is close when it comes to the real number system in the operation x, y plus x plus y. So now let's look at the general form when we are looking at closure property for some of the numbers. So for instance, when we talk about real numbers, we are looking at all types of numbers, which includes integers, which are positive and negative whole numbers. It includes rational numbers, irrational numbers, and the likes. So when we take sum, for instance, or addition, we can say let a and b, which belongs to the real number system, right, such that a plus b will also belong to the real number system, right? So it means that for sum, any example we use, so for instance, if we use 2 and 3 as the example, 2 plus 3 will give us 5, and 5 belongs to the real number system. So any example we use for addition or sum, we realize that it is close under the property of sum when it comes to real numbers. Now let's consider difference or subtraction. So if we have a minus b, we know we will get a minus b, right? And a minus b belongs to the real number system. For instance, if we have 2 minus 3, we know it gives us negative 1. And negative 1 belongs to the real number system. So subtraction as well, or difference as well, is close when it comes to real numbers. Now let's consider the product. So if we have a and b, which belongs to the real number system, a multiplied by b gives us a and b, right? ab, where we know ab belongs to real number system. Now we know that, for instance, when we are using 2 multiplied by 3, it gives us 6, and we know that 6 belongs to the real number system. So product as well is close when it comes to the real numbers. Now let's consider division. So for division, for instance, if we have 2 and 3, right, we will know that division will be 2 divided by 3. And we know 2 divided by 3 belongs to the real number system. Right, how about if you have 1 and 0, and we are dividing it such that it becomes 1 over 0? We know this becomes an undefined term. And once it's an undefined term, it doesn't belong to anywhere real number, right? So 1 over 0 doesn't belong to the real number system. So it means that division is not always close on the set of real numbers, because dividing by 0 gives us an undefined term, right? So let's consider integers. With integers, we are dealing with positive and negative whole numbers. So for instance, we have -2, -1, 0, 1, 2, right? So the dot 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 means that it goes to infinity both to the left and to the right. Now, when we consider the integers for addition, for instance, if you have an integer a and then you have another integer b, the results will give us an integer, right? So where a and b are part of the integers, a plus b also is an integer. So it means addition is close, right? So that is a sum. It is close when it comes to integers. So for instance, if I have -2 plus 1, it gives us -1. And we know -1 belongs to the set of integers. Now, how about subtraction? A minus b would also belong to the set of integers. So for instance, -2 minus 1 will give us -3. We know -3 belongs to the set of integers, right? So we can also check for products. So we have a multiplied by b, which gives us ab, right? If you have -2 multiplied by 1, it gives us -2. And we know -2 belongs to the set of integers as well. So product as well is close when it comes to integers. But then when it comes to quotient, so for instance, we are using -2 and then 1. Quotient deals with division. So it means that we have -2 divided by 1. And that will give us -2. And -2 belongs to the set of integers. How about if we turn it the other way around? So that gives us 1 all over -2. And that is -half. And we know that -half does not belong to the set of integers, because -half is a rational number, right? So it means that for division, we will not get all of them belonging to the set of integers. So it is not close under the property of division when it comes to integers. Now let's consider the closure property when you are given a table. So this table has the rule to be multiplication, right? That's the rule. And then the set is a set 0, 1, and 2. So to be able to know whether it is close, all we are doing is that when these, for instance, 0 multiplied by 0 gives us a product 0. When these products are formed, so we have 0, 0, 0, 0, 1, and 2, 0, 2, and 1. We want to see whether there is any element that belongs outside this set. So for instance, if there was a 3, or there was a 5, or there was 11, then we could have concluded that it's not close. But let's check. There is 0, 0, 0, which belongs here. 0, 1, and 2, they are all here. 0, 2, and 1, they are all here. So we can say multiplication is close under the set, right? 0, 1, and 2. So multiplication is basically close under the set here. Let's consider another example. So here they've given us variables. So the variables are A, B, C, and D. And then the rule or the operation which we are using to get the product is multiplication, right? So we want to check whether the product here, A, B, C, D, B, C, D, and A, C, D, A, and B, and then D, A, B, and C belongs to the set A, B, C, D. So pause the video and check and see whether any of them falls on the outside. So I believe that you'd conclude that all the products that we have here, A, B, C, D, B, C, D, and A, and the likes, are all parts of the A, B, C, and D, right? So we can say that the set star is close under the operation on the numbers or variables A, B, C, and D. Right? So we can conclude that this set is closed. So in this lesson, we've basically considered a very important property of binary operation, which is a closure property. In our next lesson, we'll consider another property of binary operation, which is a commutative property. See you in the next lesson.